afternoon, everyone. I'm Xiudeng Zheng, also from Institute of Zoology, and my topic is significance of one-third law in evolution of cooperation. And this is the outline. It has the 6 parts: background and the main goal, modeling process and games in finite populations, diffusion, approximation, main result, and conclusion. First, background and main goal. We know that for the evolution of cooperation among the non-related individuals, 2 basic questions are: 1, how cooperative behavior can be maintained in the population, and 2, how the cooperative behavior can emerge in an odd-factor population. Then, TFT-RT game has shown that tit-for-tat strategy could be a local NE, but it cannot be used to explain how cooperation can emerge in an RD population. And in 2004, a stochastic game model in a finite population was developed. And one-third law here is for TFT-RD game with weak selection, then the fixation probability of TFT will be larger than 1 over n if interior equilibrium is less than 1/3. This may provide a possible explanation for why cooperation can emerge in an RD population. However, a further question is what the evolutionary significance of one-third law is. What the connection between one-third law and the individual's fitness is. Our main goal here is to provide a possible theoretical analysis for the evolutionary significance of one-third law based on the individual's fitness. Second part, modeling process. In every step, choose 1 individual for reproduction and 1 for death. The offspring of the first individual, the offspring of the first individual replace the second one. And the modeling process is a birth and death process. Here, true observing space are considered all red or all blue. We denote I as number of red ball, and pi I plus 1 is transition probability from I to I plus 1, and similarly pi I minus 1. This is the probability. So the observing space are I equals 0 or n. In neutral drift, stochastic fluctuations when there are no selection, the probability that a particular individual will become the ancestor of all individuals in the population is 1 over n. This is called also the fixation probability. Effect of selection on fixation probability. Here we define a red ball is a mutant, and the relative fitness of a mutant is denoted by R. So we can calculate the fixation probability of a new mutant with relative fitness here, denoted as U. So from the initial, where this is only 1 red ball in all the population, there is the probability it will convert to all red, and 1 minus u to all blue. Part 3, games in finite population. This is the 2 phenotype games with strategy A and B. So we define the payoff matrix here, and we can calculate the expected payoffs. Here N is the population size. Population defined population with fixed size and we 2 phenotypes A and B, and 2 observing space, all red or blue. we denote I is the number of players of type A, minus I is the numbers of B, and the fitness of A is Fi, fitness of B is Ti. So here omega is defined as intensity of selection. Fluctuation probability of stretch A, it is calculated here. If U is bigger than 1 over N, then we say the selection favors A replacing B. And if it's more than 1 over N, we say the selection opposites A replacing B. This is the one for here. X star here is unstable equilibrium, which is this expressions here according to the payoff matrix. So if X star is more than 1 over 1/3, then U is bigger than 1 over N for large population size and weak selection. For diffusion approximation, if we denote X equal I over N, then we can get the continual function of the fitness A of A and B. And the relative transition probability also can get here. If we define phi xt as probability density distribution, that the frequency of A equals exactly x at time t, then we can get a focal point equation, also called forward Kolmogorov equation. Here D1 is the street diamonds and D2 is the diffusion one. If pi plus and pi minus is the transition probability. Similarly, if we find probability density distribution that the frequency of A equals exactly x at time t with initial state t at time t equals 0, we get the backward equation. Five main results. Here we will introduce 4 definitions here. Fixation probability that is introduced before, and mean fixation time, mean effective fixation time, and average fitness about the mean effective fixation time. One fixation probability of status A. If we UPT as probability that A is fixed at time t given its initial frequency p, then we can get the backward equation with the boundary conditions here. By solving the above equation, we can get the expression of UP under weak selection. If A and B are both strict on E, then alpha bigger than 0 here, and so UP by bigger than P if X star is smaller than 1 minus P over V. For large population size, then we get the 1/3 law. U1 over O is bigger than 1 over O if X star is more than 1/3. For TFT OD gain, here we denote A as TFT, B as OD, and the payoff matrix is here. B is benefit, C is the cost. So selection can favor the TFT replacing OD. If X star here is more than 1/3, then E is bigger than 1 over O. 2. Mean effective fixation time. Here we define theta as density function of time t until absorbing x equals 0 or x equals 1 occurs given the initial frequency p. that T is the initial frequency. Then we also get the backward equation, but the boundary condition is they are all zero. Here we definition mean fixation time with the initial frequency T is defined as T bar T is integral with this. Because this integral is finite, we have it turns zero as T turns in Diffusion. So we can get this equation with boundary conditions or are wrong. The solution of the equation can be expressed by this detail is here. So if we consider the large population and the quick selection here, large population and the quick selection, we can get the expression of T. So this is the mean fixation time. It means the mean fixation time until either x equals to 0 or x equals to 1 occurs. Next, we can define the mean time that the frequency of A spans in the interval x1, x2 before observing. So it's x1, x2. And also, similarly, by times the transition probability, we get the mean time that the system states jumps from x to x minus or plus or minus 1 over n, 1x is in the interval x1, x2. Since this equation, so we call this expression as the mean effective time that x spans in the interval s1, s2. That means the time, the state of the system is changed. So this is the mean time of effective. This is the jump from x to x minus 1 over n is jump from x to x minus 1 over n. Next, we define the mean effective fixation time until the observing boundary x equals 0 or x equals 1 is reached using the initial frequency of A to T. This is the equation. If the selection is weak, then we can get the expression of tau P. If P equals 1 over n and the selection is weak, then we can find that tau bar 1 over n equals to 1 minus 1 over n. This is mean effective fixation time. Here it comes with transition probability. Mean effective fixation time until the boundary occurs. We also define the mean effective fixation time into two parts, tau 1 and tau 2. Tau 1 means that the mean effective fixation time of meeting A individuals before observing, and tau 2 meeting B individuals before observing. Then under weak selections, we can get the expression tau 1 approximately equal 1/3 minus 1/3 times n square. So, and this is tau 2. The average fitness about the mean effective fixation time. Average fitness of straight A about mean effective fixation time tau bar T is denoted by F bar here. And under weak selections, we can get the expression. Similarly, we can get average fitness strategy B about the new effective fixation time tau B is denoted by G bar. And also under weak selections, we can get this expression. For weak selections and large population size, when P equals 1 over N, we can calculate the difference between F and G as the expression here. So we call this, it is the significance of one-third curve based on average fitness or the mean effective fitness because we get that under weak selection, the difference is still like 0 if F star is more than one-third. That this exactly matches the one-third law. So conclusion for TFT or D-game in finite population with size N and weak selection, one-third law is not only means that the fixation probability of TFT will be larger than 1 over N, but also that the average fitness of TFT about the mean effective fixation time will be larger than that of all D. So thank you.
So let's thank to Dr. Xiudeng Zheng. So any questions? Please.
Thank you for your talk, and I think I have proved the similar thing in 2006 or 7 with Martin Novak, and that says if the average fitness of strategy A is greater than the average fitness of strategy B over the course of until fixation. So you can define the period where the fixation doesn't occur. And during that transition period, if the average fitness of A is greater than B, then this condition is equivalent to the one-third law. So maybe you are interested in looking at my paper also.
Yes.
So, thank you.
In Novak's work, they are considered in the marine process. I'm sorry. In his work, in his research, he do research on the marine process. Yeah. So it is based in the finite population size. So he can calculate the transition probability exactly. Is the discrete. Is the discrete situation. What we consider here is the continual integration. And that's the differences between our term and his.
Okay, any other comments? So may I add some comments? Because as far as I know, there are at least 3 papers studied a similar problem. So your paper and Oski's paper and also another paper by Sabine Sartre, I guess. So you know that? So could you briefly compare your method and the Sabine Sartre's method? Because you just compare your method and the Oski's method.
My method here is based on the forward and backward equations. But I think Sartre's work is based on, in my view, its calculus is very complex.
Okay, thank you. Let's thank you.